Okay, so this problem here, what we consider is that there are multiple forces exerted on the object. Okay, so last time we have listed the equations. So the equations we have listed, was, okay, so I probably need to write those down again, but anyway, so that's the equation we have listed was this one. Okay, so we have 200 cosine 30 degrees times I hat plus 200 sine 30 degrees times j hat, right? And so on. And F2 equals negative 300 cosine 45 degrees. You have those equations in your notes, right? Here, just 300 sine 45 degrees j hat. And then F3 equals negative 155 cosine 53 degrees times I hat, then minus 155 and sine 53 degrees times j hat, right? So then you sum up for each component, you get a sum, and you will get something like this. You will get F1 equals 100 square root of 3 times I hat plus 100 times j hat, right? Once you substitute in the numerical values, and F2 will be equal to a negative 150 square root of 2 I hat plus 150 square root of 2 j hat. Sorry, I need to change to a different marker. And F3 equals negative 93 times I hat, then minus 124 times j hat. How did I obtain those values? So basically what I used was consider, for example, if you want to get cosine 30 and sine 30 degrees, so you consider this right triangle, right? And here on this side, you have square root of 3, you have 1, and here you have 2. And therefore, you can write down cosine 30 degrees will be square root of 3 over 2, right? And sine 30 degrees will be equal to 1/2. I know that some of you just use calculator to get the output, right? But even without calculator, if you see an angle like 30 degrees, you can write down the expression without calculator. So sometimes you need that, right? And for example, if you are going to take statics after this course, okay, very often in order to speed up your computation, very often you need to have this kind of picture in mind. Okay? And now, what about 45 degrees? When you have 45 degrees like this, what's the quick way of getting cosine and sine? Right? So consider this side, the base as 1, height as 1. What's the hypotenuse? Square root of 2, right? So therefore, cosine 45 degree, in your mind, you can just directly write down 1 over square root of 2. That would save your time. Some people will write it down as square root of 2 over 2. That's the same thing. But okay, and then sine 45 degrees would be equal to 1 over square root of 2 as well. Right? So that's how we did the computation. That's how I did the computation, right? How I got those numbers here. Then how about 53 degrees? Again, for statics, that course, this is also very important. Very often you will see this. 53 degrees here, right? And then if I assume the base to be 3, and then for 53 degrees, approximately this would be 4. And then what would be the hypotenuse? 5. Okay, that's great. So therefore, cosine 53 degrees would be 3/5. And then sine 53 degrees would be 4/5. Right? And this triangle is approximate. That means when you have 3, 4, and 5, that 53 degrees is approximate. This value is approximate, right? But it's close enough. We can use 3. When you see a right triangle of the sides 3, 4, and 5, you know that this angle is 53, and the other angle is 37, right? So that means when you see, you can also obtain cosine and sine 37 as well. Okay? So, but anyway, so that's just some heads up, some formulation you can use. Again, that's why I mentioned that geometry is very important, right? So if you have those right triangles in mind, And you can just write down the expressions directly. Of course, you may need to memorize some numbers here, right? But then it will help you speed up with the calculation. Then you can do the sum. The rest will just be computation. The rest will not be difficult. And then, let me erase this. So once you get the sum, you will get, you'll get this F net. The net force will be equal to 100 times square root of 3 minus 150 times square root of 2 minus 93. Okay, combine all the x terms, x components, and then also get the sum of all the y components. That will be 100 plus 150 times square root of 2, then minus 124 times j hat, right? And then you can carry out the numerical values. It will be like this one. It will be like negative 131.927 times I hat, then plus 188.132 times j hat. Okay? X and y components. So now we can interpret the components. We can call the first component, call it fx, right? So last time I only wrote down the expression fx plus I hat plus fy times j hat, right? But today I also give you the numerical values like here. So you know this is fx, right? And this is fy. And then what you can do is find out the magnitude and direction, right? Find out the magnitude and direction. So, and make sure you keep working on the homework, okay? Keep working on the homework because it's very important, right? And I will post a new one. Once we enter chapter 2, like today, hopefully we can start chapter 2 a bit. Once we enter chapter 2, I will post a new homework assignment as well. Okay? And so now let's consider about it. Consider the magnitude. So magnitude of f net would just be equal to use Pythagorean theorem, right? The square root of fx squared plus fy squared, and therefore once you carry out the numerical values, you'll be about like 230 pounds. Okay? About 230 pounds, and that would be the magnitude. Then now let's consider direction. Right? Direction, you consider tangent theta. So we did this before. Tangent theta equals fy over fx, right? So that would be fy over fx. So that would be, so let's consider this ratio here. So here you have 188 as fy, okay? And negative 131 point something as fx, right? When you take this ratio, then you will be able to get a numerical value like negative 1.42603, something like this. Right? Here I intentionally keep more figures because in the end, of course, I will round off. Right? In the end, I try to keep 3 significant figures, but in those intermediate steps, I try to keep more figures so that the result can be more accurate in the end. Right? But anyway, so now we have tangent theta equals this. So 1x. Once you have obtained tangent theta, 1x. We want to obtain theta, right? We want that angle. So inverse tangent, right? So that's great. So, but before I do the inverse tangent, I would like to know what the vector look like, right? So that's something we talked about that before. We talked about you can use some parallelogram method to consider where's your f net, right? That's something toward the end of the previous lecture. We talked about that before already. So suppose now you know that after you use the parallelogram method to do the sum of the 3 vectors, conceptually you will know that your f net will be somewhere here into the second quadrant. I think that makes sense, right? You agree? That makes sense because your fx is actually here, right? That x component is actually here, and fy is here. Right? Fy is here. So therefore, which angle are you going to obtain? So first, you need to be clear about the goal, right? So which angle do you plan to obtain from here? It's this angle, right? This angle here, this angle. angle theta here. Right? That's what we try to obtain. So that's why we wrote down this. Right? It's because of the geometry here. Right? So now we try to obtain arctangent. Right? Now we know that we try to obtain arctangent. So arctangent of this thing. This thing. So you will see the output, right? And what would the output be? You'll be right. So that's great. So you'll be negative of about negative 54 point something degrees, 0.96 degrees. Right? So, but now apparently this is not theta, right? This angle is not theta. This angle is actually, what is this angle? It's some other angle, right? Some other angle. So now let's look at that angle. It's a negative angle. So that angle will be, you do the backward extension of this vector to here, and that negative angle will be this one. You can call that omega here. Okay, so this is actually omega, some angle here. But now the next thing is we try to make it positive. So therefore we try to obtain this angle phi instead of omega. Okay? So we want to obtain this angle phi here instead of omega. So phi will be here. So phi is something we can call it as a reference angle. Phi, so let me put it here. Okay, this angle is called phi here. Okay, so phi and angle, they are the same. The phi and omega, they are the same in magnitude. So phi equals absolute value of omega, and that's 54.96 degrees, right? And then once you have obtained phi, what's the relation between theta and phi? Because the ultimate goal is to obtain theta here, right? Right. So they add up to 180. So you have theta plus phi equals 180 degrees. Therefore, theta will be equal to 180 degrees minus phi. Right. So 180 minus phi is about 125 degrees. Right? So in the end, we only keep 3 significant figures here. So now our answer would be angle. Okay, that direction is 125 degrees, and the magnitude is 230 pounds. So that completes the part A of the problem. Okay, so this is only part A. Okay? Part A of the problem. But part B, the idea is as follows. The idea is you need to add one more force so that the new resultant force will be 0. Okay? So that's the goal is you add one more force so that the new resultant force will be 0. So what's that one more force you need to add? Okay, so any idea? The opposite. So that's great. Okay, so any other suggestion? Yes. Yeah, so that's also the right answer, right? So that's great. So the idea is you are going to add one new force so as to cancel out the old one. Right? So once you add one more force, the old force is canceled out exactly. Okay? Completely canceled out. So that means that not one new force must point into the opposite direction. Say your old force is here, right? Then your new force must point into the opposite direction so that it totally cancels out the old one. So do you agree? Yes. So okay. So hopefully there's no disagreement. So now we're going to finish this one. Okay? So part B, we have finished part A. Part B, it's not too bad. I mean, it's not too complicated if you have the concepts. That's why we say that the senses of geometry is very important. Right? If you have the concept, you can answer that question very quickly. The magnitude would just be the same, but the direction would point into the opposite direction. So you can figure that angle easily. Right? That new one is here, and that reference angle associated with the new one will be just this phi here. But now here, we're going. If you want to do it rigorously, here I try to do it rigorously. I mean, step by step. What's the step that you need to follow? But of course, you can use concepts to answer the question. That's also fine, right? But if you want to do it rigorously, you do this. The OF net. Okay, so this F net is the OF net plus the new vector equals 0 vector. Okay? So the new F net is 0. Okay? Here 0 hat means all the components are 0. So therefore F4 should be equal to negative of F net. So that means you need to grab the two components of your F net and multiply it by -1. So sorry, I have erased the old one. So, but it's okay. So I'll just write this down here. Okay, negative of your f net. So then the two components will become positive 133.927 times I hat minus 188.132 times J hat. So that will be your F4. Okay? So pounds. As you can see that F4, you have the X component to the right, and Y component is down, right? Y component that is negative is down. So therefore, F4 apparently points into the fourth quadrant, right? Fourth quadrant. Now let's check what's the magnitude of F4. Magnitude of F4, you will see that magnitude of F4 would just be equal to, use Pythagorean theorem. I'm sorry, this is F4 comma X. Sorry, this is 4. So please change the subscript. Okay, so I didn't write it precisely. F4 comma X, F4 comma Y here. So therefore, you use Pythagorean theorem, and you will see that this F4 comma X squared plus F4 comma Y squared, and this result would just be equal to, you take a square root, right? And this result would just be equal to 230 pounds. Same thing, right? Because you can see that the signs will disappear, right? Here you have positive, you have negative, but once you square it, those signs disappear. So that's why the magnitude would just be the same magnitude as your OF net magnitude, right? So that verifies the argument, yes. Yes, I will be clear. Right? I will be clear. I mean, on a test, if I ask about an angle, I will be clear that whether I ask about angle in standard position or reference angle. Okay? I will specify on a test question. Yeah? So that's a good question. Yes. Okay. So now we have gotten this. Now let's try to obtain the angle in standard position for your F4. Okay. So although some of you have already answered correctly, it's just this angle, right? But we tried to, sorry, this was the reference angle. So some of you have answered it correctly. So now we wonder what's the angle in standard position for that F4. So now let's draw F4 here. Okay, F4 is actually here. So I would suggest you start with a new figure, but here I just draw it here. Your F4 is actually here, right? F4 is actually here. So now we want the angle in standard position for your F4 here, right? So therefore, let me erase thing. Let me erase this. So if you want to follow a strict procedure to get that angle we can call that theta 4. Let me draw it again here. So your F4 is here, right? Your F4 is here. So the angle we want is this angle here. Angle in standard position, theta 4. Right? So now let's see how we got this. How we can get this. Tangent theta 4 equals F4y over F4x. So now let's consider this ratio here. Here you have negative 188 point something, right? Negative 188.132 divided by positive 131.927. And this ratio, you can see that even though the y component now is negative and x is positive, but the ratio you will still get the same ratio, which is negative 1.42603, right? And then when you try to obtain arctangent of this thing, then you will still get negative of 54.996. Right? And then we know that this negative angle we can call that omega. It should be this angle here. Right? We got this angle omega here, and this is the omega we obtained. Okay? So then you follow similar procedure. You can try to get phi 4. So phi 4, let's say phi 4 is this one. Okay? Phi 4, that's the reference angle. So phi 4 equals absolute value of your omega, so that will just be equal to 54.96 degrees, right? And once you get phi 4, then what's the math for you to get theta 4? What's the math? what's the equation? What's the equation? Basically, we are asking about the equation. So what's the relation between theta 4 and phi 4? Yeah, so you have theta 4 plus phi 4 equals 360 degrees. Right? So this one. So again, if you compare this case we use this equation. It's based on geometry that we have, right? This case, let me erase F4 here, right? This case, the old case, we just use this equation, came from geometry. Again, this equation here came from geometry as well. It's a different equation. So if you're not familiar with geometry, you may get confused. Very easy, right? So therefore, what is your theta 4 would be equal to 360 degrees minus phi 4. And then you will get the answer. The answer will be about 305 degrees. Right? So now this is the final answer. The magnitude, part B, the magnitude is also 230 pounds, and the angle is 305 degrees. Okay? So on the test, I'll be clear which I'm asking about. I will be clear that if I ask about angle and stand-up position, then you answer this one, right? So this is angle and stand-up position, and this is called reference angle here. So now let's move on. Okay, so this problem we have completely finished that. So now this one, we try to spend some time on it, but not too much. This is a short question. This one. So that's the last question I will talk about here for the chapter. So there are two persons. They are trying to move an object. So one man exert a force F1. The other man exert a force F2. But now there's a boy. That boy is trying to exert a force somewhere to somewhere, so that now we try to obtain the smallest force that boy should exert in order to let the motion of the object to be directly toward the right. Okay? We want the motion to be toward the right. So that means the net force need to be pointed just toward the right, right? But if you try to use parallelogram method, you see that the net force is not to the right in this case, right? I mean, without the boy, without the third force, the net force is not to the right. So we try to solve this problem, right? Try to solve this. Do you get the idea behind this, right? So again, this was not from our textbook, from a different book in the 60s, 1960s. But this is quite very interesting question here. So now, how do we solve this problem? So again, different persons may have different ways of solving this problem. I mean, the method may not be unique. I mean, the line of thought may not be unique. But now let's try to see how we consider such a problem here. Okay, so this problem, if you would like to consider this quickly, we do the following. You consider a free body diagram. Okay? So practice question 3.4.d. And consider this diagram here. There's a x and y coordinate system, x and y, right? And consider this object as a point here. Right? Although it has a structure, but though we can ignore the so-called irrelevant degrees of freedom, just consider this as a point, and multiple forces are exerted on the same point. So one force is here, right? And the other force is here. So here, let's just do it conceptually. So here I just share with you my method, right? Because you may have a different method. It's fine, yeah, as long as you achieve the correct answer. And so now here, this angle is 60 degrees. This angle is 30 degrees, right? And here you have F1 and F2. Let's say F1 is here. So you decompose your F1 onto two components, here and here. Right? And the second part is you decompose your F2 also into two components, here and here. Right? So this is F1, this is F2. And we know the magnitude of F1, right? Magnitude of F1 is 100 pounds. Magnitude of F2 is 80 pounds. Now, the consideration is the x components of F1 and F2. You can write them down very easy, right? X component and y components. X component will add up, right? They are both toward the right. So x component of the two forces will not affect your answer, right? Because those forces will just directly toward the right. That's what we want. That's the desired component, right? Those are the desired components, right? That's what we want to keep. But now the problem comes from the vertical ones, right? There's one up, one down. And they don't cancel each other, right? So what's the goal of the boy? The boy is going to exert one additional force. At least they want to the force of the boy, at least he wants to cancel out the y components of the two forces, right? So you can consider, do you get the idea? Y components of the two forces, if the boy add the third force, then that y component of that third force is going to cancel out those two exactly, so that there's no, so all the y components will vanish. Basically, the net force, the y component of the net force will vanish, right? That's the goal. So do you get this part, right? So we want that y component to vanish. So now let's just analyze the y component, because we know that the y component is the key, right? Is the key to the end. So let's look at this one. The F1y, we can write it as, since the magnitude is 100, right? Angle is 60, so we can write it as 100 times sine 60 degrees, right? So that's the y component for the first man, okay? First man. And the y component of the force for the second man, how do we write it down? F2y. So we can somehow start with, the magnitude is 80 pounds, right? And then angle is 30, so if you consider the y component should be something like 80 times sine 30 degrees, right? Is it right? 80 times sine 30 degrees. Do we miss anything? Yes. What do we miss? A negative sign. Hey, that's great. So we miss a negative sign here, right? So now, let's try to finish the computation here. So this question is short. As long as you have the concepts, this question is actually short, a short question. So now we try to achieve the minimum force from the boy. So the boy, of course, that force from the boy can also have an x component, right? But if it has an x component, then it's not a minimum force because it already has a y component, right? And so that means the minimum force should contain only the y component. Minimum force from the boy. So that's why it's clear to say that the force exerted by the boy, the minimum one is going to have only the y component. We can consider that as F1y plus F2y. So that's 100 times sine 60 degrees minus 80 times sine 30 degrees. But remember, this is something we want to cancel, right? We want to cancel out this part. So that means this component, we multiply it by -1. Try to cancel it, right? That remaining component, after we get the sum of these two, that remaining component, we want to cancel it. So multiply it by -1 and multiply it by j hat. So that's what we want here, right? So now let's do the algebra. If you do the algebra correctly, you will see that this is negative of 100 times square root of 3/2 minus 80 times 1/2 times j hat, right? Then you do the algebra, you will see that this is negative of 50 square root of 3 minus 40 times j hat. And if you consider numerical value, you'll be like negative of 46.6 and times j hat, and will be in terms of pounds, right? So now you can see that what's the magnitude of the force exerted by the boy? It's just 46.6 pounds, right? And the direction will be downward. So is that clear? Right? So the magnitude of this, the minimum force, right, will be 46.6 pounds, and the direction is down, right? Direction is down, okay? Downward. That's it. That's how you answer such a question here. Okay? Okay, so we finished this question as well. And so chapter 3, I mean, my explanation has been finished, right? So then you keep working on the homework here. So for the homework, the last 2 questions will be about a section called section 4.6. But for section 4.6, on Friday, I will try to explain about that briefly. But we don't plan to cover that whole section. So it's in chapter 4. That title is called relative velocity. Okay? Relative velocity. It's a more difficult section, more difficult. But it's relevant to chapter 3, actually. That's why I put it after chapter 3. But we need to know the velocity first, right? So that's why we don't talk about this right now. But on Friday, I will cover that information. Okay? The last 2 questions of this first homework will be relevant to this section, but also relevant to your daily life experience as well. So if you have read through that, you know that. So now, my plan is to start with chapter 2, right? And at some point, when we have sufficient information about velocity, and then we come back to talk about those 2 questions. Okay, those 2 questions, how to solve that 2 questions in the homework as well. I don't plan to cover the whole section, this one, right? But chapter 3, we have finished it, so we are going to move on to chapter 2. Chapter 2, I didn't upload the slides because I'll present on the whiteboard first. Right? Chapter 2 here. Chapter 2, the main point will be from 2.7 all the way to 2.9. That's the main point where we have the main points here. But of course, the prior sections are also relevant, right? So that's it. Okay? So that's the idea. Let me erase some things. Today we will start, but so today I'm almost not using any slides, okay? But just use slides to present the title. But I will write down things on the whiteboard. For chapter 2, I almost do not use any slides for chapter 2 today. But of course, on Friday, we may use some of the slides. All right, so now what we really care about is as follows. In this chapter, we are considering the so-called motion in 1 dimension. So we consider an object, a rigid object, and usually we want to treat that object as a particle. So by particle, we mean that, so like I have an object here, right? And suppose I can exert a certain force on the object, so that this object can move with, let's say, a constant acceleration. So if you start reading from section 7 of the book, you will see that they will try to explain to you what are the so-called kinematic equations regarding an object moving with the constant acceleration. But before we do that, of course, we need to understand what we meant by acceleration, right? So like those 3 sections here, right? And this 2.7 here, we are going to show you several kinematic equations. And the derivation, those are in section 9. Right? So this is section 7. And equations are laid out in section 7. The rigorous derivations are shown in section 9 here. So now let's consider the following thing. Let's start with the first equation here. Okay? Let's start with the first equation here. So how do we consider that first equation? So I'm not following the slides. Okay? I'm not following, but here I just show you that if you read the textbook, you will see those equations. But I'm not following the slides. Here I'm considering the following. You consider section 2.7 and section 2.9 together. Okay? Consider those 2 sections together. And afterwards, we'll move back to section 8 of the chapter here. So here we have information in chapter 2 here. So the consideration is as follows. First, we need to consider, we have learned about vectors, right? So if you consider a motion of an object in 1 dimension, say I have an x-coordinate here, and I have the origin, right? And the position of a certain particle or object, suppose that initially is located somewhere here, some initial location, right? And at a later time, that particle is moved to a different location called find some final location here, x final. Then we will be able to define the so-called velocity of the particle. So velocity, we can start with defining some average velocity. Some average velocity can be defined as the following. Suppose at initial time, t initial, the location is called, position of the particle is called x initial. At some final time, t final, the position is called x final. So we can first define some average velocity, let's call it, say, v bar or something. And it's defined as the final position minus the initial position divided by the final time divided by the initial time. Right? So this is sometimes called as delta x over delta t. And to memorize this kind of equation, you can consider this as some displacement over some time interval. Okay? The displacement over some time interval, the associated time interval, then this ratio is called average velocity. Okay? So this is called average velocity. The textbook, they have something called AVG, but here I use a bar, which is easier, okay? So to save time. So this is called average velocity for a particle, for motion of particle, right? So now the next step is, once you have average velocity, you can define a so-called instantaneous velocity. So instantaneous velocity can be considered as, once you have this ratio here, if you try to make your time interval to be smaller and smaller, and you can take a limit like this. Take a limit of this ratio and make the delta t smaller and smaller so that it approaches 0, then this ratio will give you the definition of instantaneous velocity. Okay? But this is most likely high school information, so that's why we go through those very quickly. Okay? So very quickly. Other instructors, they will also teach in the same way, in a similar way. Right? We go through those basic material very quickly, then we come to the main point to derive those equations for you. And then we'll show you the applications as well. So this is the so-called instantaneous velocity. Right? So that this is true for a particular time. So this instantaneous velocity we can consider as it would be associated with a particular time instant, v as a function of time. Right? If you know about calculus, you have seen this equation, dx dt. Right? So instantaneous velocity can be considered as the time rate of change of position. So we use calculus. If you want to use calculus, then you have dx dt equals instantaneous velocity. While the average velocity, you consider the displacement, consider this as the displacement over the time interval, right? So that's the difference. Then how about acceleration? Once you can define velocity in this way, then your acceleration, instantaneous acceleration, can be considered as dv dt. The first time derivative of velocity, you will see acceleration. And acceleration can also be considered as follows. Since velocity equals this, right? So this can be also written as the second time derivative of position with respect to time. That's what we mean by acceleration. Okay? Velocity, acceleration. Okay? Velocity is the time rate of change of position, and acceleration is the time rate of change of velocity. Okay? So that's what we can show you right now. And next time we are going to show you some kinematic equations for constant acceleration. Here, acceleration may or may not be constant in general, right? But now we are going to, afterwards, we're going to restrict ourselves to constant acceleration. So thank you all, and see you again next time.